Good morning, good afternoon, and good evening, wherever you might be joining us from today. My name is Susan Christoffersen, and I'm a professor of finance at the Rotman School and one of the co-directors of Rotman's TD Management Data and Analytics Lab. Thank you so much for tuning into our live stream today. Although we are having to meet virtually, we wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. We also stand in solidarity with the ongoing efforts to dismantle systemic racism and discrimination. So this morning, we are very fortunate to have 4 experts joining us today to share their observations and knowledge about the challenges facing supply chains and how AI and data analytics could be used to improve these efficiencies. I really couldn't think of a more relevant topic for us to be discussing in today's environment. The world is facing unprecedented challenges in managing supply chains. It's really hard right now to open up a newspaper or watch the news without reading or hearing something about stresses in supply chains. The challenges are wide-ranging, whether it's concerning issues of vaccines, medical equipment, food, manufacturing supplies. I know before the pandemic hit, many of us probably had never seen stores with empty shelves, but we were quickly reminded of how dependent we were on these essential lifelines for our economies. More recently, we've witnessed how natural disasters, civil unrest, blocked transportation lines, cross-border trade restrictions only serve to exacerbate weaknesses in supply chains. So today's speakers look to provide some insights on how firms can better manage these risks and what the potential benefits and limitations of using AI and data analytics in trying to manage these different risks. And of course, AI and data analytics aren't going to solve all of our problems. And so understanding, which risks are better suited for these new techniques to manage inventory or logistic issues. So I'm going to stop there because I want to leave as much time as possible for our speakers. But before turning it over to today's moderator, I first want to remind you that throughout the sessions, you're going to have opportunities to provide your Q&As. You can enter your questions on Zoom, directly on Zoom, or if you're watching through YouTube, there's also an opportunity for you to provide your question and answers there. And our moderators and speaker will try to address them as best as they can. I also want to recognize that this event is hosted by TD Management Data and Analytics Lab at Rotman, and it is sponsored by Kinaxis. And Kinaxis is a leading provider of cloud-based supply chain planning software for Fortune 500 companies around the world, and recently was named a leader in the 2021 Gartner Magic Quadrant for Supply Chain Planning Solutions. And I really couldn't think of a better person to moderate today's event than Brian Keng, who represents both these organizations and has been the mastermind behind the scenes pulling together this terrific lineup of speakers. For those who don't know Brian, he is the chief data scientist at Kinaxis with a deep knowledge of the many issues and the AI technologies being discussed today. While being a chief data scientist for a large company might be enough for one person, Brian managed to spend some of his time with us at Rotman working as a data scientist in residence at TD's Management Data and Analytics Lab and teaching in our Master of Management Analytics program as an adjunct professor in data science. We're also very proud to call him an alum of U of T, having graduated from our computer engineering PhD program. So with that, I'm going to turn the mic over to Brian, who will be moderating this morning's event and providing you with an overview of what to expect and introducing our 4 experts. So please join me in extending a warm welcome to Brian and our 4 speakers today. Brian, the virtual stage is yours.
Great, thank you so much, Susan, for that great introduction. And I am so excited about today's events. As Susan mentioned, I'm actively working in these 2 areas, so I'm so glad we could put such a great lineup of speakers together. So just a little bit of housekeeping. The format for today is for our 4 speakers, they're each going to have a 30-minute block, approximately which 25 minutes will be their main presentation, of which we'll have 5 minutes at the end for questions. And I'll be selecting the questions for that 5-minute Q&A period. So make sure you get them on there, and I'll try to select the ones that are most relevant and popular. And with that, on behalf of TD Management Data Analytics Lab, as well as Kinaxis, I'd like to present our first speaker, Simai He. So a quick introduction for Simai. He's the chief scientist at Cardinal Operations, a leading OR-oriented startup company in China, providing end-to-end solutions for retail, logistics, and manufacturing. He's also a distinguished professor in the Department of Management Sciences at Shanghai University of Finance and Economics. Simai is going to present some case studies on applying the technology from Cardinal Operations to clients in Asia, particularly addressing volatile periods such as COVID and the pandemic. So please welcome Simai.
Thanks, Brian. And good morning, everyone. I'm great honored to be invited to this exciting event, and I would like to thank our colleagues in Rotman Business School for organizing this event. So today, I would like to share our experience about how AI and data technology have helped us to improve the supply chain management efficiency, and especially fighting the pandemic during this recent crisis. This talk has been organized into 2 parts. To begin with, I would like to give a very brief introduction about Cardinal Operations and share our opinion on how AI and data technology have helped supply chain management. Cardinal Operations have grown to be one of the leading business intelligence firms in China. We are focusing on supply chain operations. In this big data era, firms are accumulating enormous amount of data, which are costly to collect and manage. So they're more than eager to utilize the data to create value from this data. From the raw data to business decisions, it usually takes 3 steps. The descriptive analysis, which collect and process the raw data to explain the past and gain managers' experiences. The predictive analysis, which use statistical and AI technology to forecast the future. And the prescriptive analysis, which uses model to help making decisions and gain managers' insights. The last step is often the most valuable to business, and it is where operations research and operations management experts are needed. We have been serving more than 100 firms with some leading firms within the supply chain industry. We provide business intelligence decisions and help firms to build smart decision platforms. Our core strength is a combination of strong data analyst team, operations management experts with industry experience, and self-developed optimization solvers for tackle different and complex problems, which are not suitable for general purpose solvers. Actually, our optimization solver COPT are now top ranked globally. Our Simplex solver has been ranked #1, and our barrier linear programming solvers are also ranked #2 in the world. Next, I would like to introduce 2 case studies from Asia of how supply chain management can help to fight the pandemic during COVID-19. First one is about the unmanned warehouses, about JD. The second one is a data-driven management system. The supply chain is very crucial to better the pandemic and get our life back to normal. We can see that during the pandemic, the supply chain has been suffered greatly and need to face challenges due to high uncertainty caused by demand side, the supply side, the delivery service, and also the uncertainty in the lead time. All these together created a great challenge in the supply chain management. However, as we can see in China, the supply chain helped us greatly to respond to the pandemic and to ease the COVID-19. We can see that the success in the during the fighting of COVID-19 is mainly due to, first of all, the quick response. We can see that the supplies, especially the medical supplies, are sent overnight, and hospitals are even built within 10 days. Furthermore, we can see that the reliable last mile delivery service helped us greatly for the success of the strict quarantine policy. My personal experience actually is that my whole family was in quarantine for 14 days without leaving the house. And we have to rely solely on delivery service for our household supplies. We further stayed in our house for several months and only need to shopping for food once several days. So, how did we do that? The first case is about the unmanned warehouse of Downe, which uses the AGVs to pick shelves to workstations. I'm sorry, there's some delay about the screen. We can see that in Downe, they built lots of unmanned warehouses. Inside those warehouses, they use AGV to carry the shelves to workstations and use human or robots to pick items from those shelves. Our team worked closely with Downe to develop the operational system, which includes order dispatching, AGV routing, warehouse layout, etc. The order dispatching systems first need to include we need to match the orders to certain shelves and then match to certain AGVs for pickup service and then send to certain workstations. All these need to be integrated into the routing decisions of the AGV. So first of all, we need to model this into a mathematical programming problem and to solve it quickly. And to reduce the problem size and to meet the real-time solving requirement, we need to utilize the intelligent partition theory first introduced by Professor Yin and Professor John Carson to decompose the working area into optimal partitions with balanced workloads, and to avoid collision of AGVs and to reduce acceleration and de-acceleration of those AGVs. We need to adopt the time-space network flow model to optimize the routing decisions of those AGVs. The performance is great. Actually, we managed to solve the problems with millions of variables and constraints within 2 seconds. In practice, the unmanned warehouses are quite efficient. It is about 50% more efficient versus human labor in normal time, and during stress tests, it's 6 to 10 times more efficient versus human labor. As for now, JD has built more than 100 unmanned warehouses. Z estimates that it has saved more than $1.62 billion in the past 5 years. And it will continue to save $3.78 more billion in the next 5 years. It also helped greatly in the battling of COVID-19, especially during the first months, as the manned warehouses could not function in full power. Luckily, this case has also been recognized by the community and is now in the finalist of this year's Informed Friends AUTOML Prize. The second case focused on replenishment planning and inventory decisions. During the pandemic, every state wants to secure enough medical supplies, but there are just not as many in the market. So the states are competing with each other. It raised harsh competition among those states, and actually it's a waste of resources. A classical way to ease the replenishment pressure is to pool those inventory together, which can greatly help to reduce the total safety stocks. For example, if all the states want to meet a desired level of service guarantee, say 99%, then if they want to order separately, the total demand would be quite high. But if they choose to pool their risks together and order together from a centralized planning system, for example, the CDC, the inventory level could be greatly reduced. As an example, we can see that if we have 4 firms or 4 states, each want to meet their 99% service guarantee, then they totally need to solve about 120,000 units. However, if they can manage to pool their inventory together, they only need to order a much less percentage, which is 20,000 units. As you can see that if you can pool your inventory together, you can enjoy about 1/3 reduction on the inventory. Actually, with more firms or more branches ordered together, you can enjoy a much larger service rate. Therefore, to manage a complex supply chain network and to guarantee agile and robust service, we should integrate the inventory decisions together. Furthermore, for the complex supply chain network, we also need to not only to pool their inventory together, we also need to integrate the demand fulfillment decisions together, as well as those vehicle routing choices to fulfill the small retailers on time and to face those challenges like factory shutdown, volatile demand, interruption of warehouses, etc. to meet those quick, agile, and robust responses. This second case is a work together with a global leading consumer good company for their replacement plan. For this module, we use operations research techniques to construct mathematical models to decide how to allocate inventory from brewery to DC under rigid and complex constraints. Replenishment planning is rolling based. Ahead of 2 days, we modify the D-2 plan. Ahead of 2 days, we do the planning without track arrangement. And ahead of 1 day, we modify the D-2 plan with consideration of the updated information, for example, the stakeholders' feedback. And also we need to take track arrangement into consideration. And then on the shipment day, we do the tail volume adjustment for TMS execution. Original replenishment planning method of the firm is purely heuristic. Planner linearly takes multiple constraints into consideration, and he or she needs to try back and forth in order to find a feasible and acceptable results. Compared to the heuristic methods, operations research is integrated and holistic. It can take multiple constraints and objects into consideration at the same time and output an optimal result. It is more efficient, as we will show, and the solution quality is much better. The original inventory positions actually were calculated based on traditional safety stock model, but it relies on the underlying assumption that the demand forecast error follow those Gaussian distributions. Moreover, it was updated only monthly or quarterly, so it cannot quickly adapt to the seasonal market fluctuations. In practice, we adopt the SDS policy with quantile-based methodology to calculate those positions. And we update it daily along with demand forecasts. Moreover, this method is not based on those assumed distributions. In practice, distributions with heavy skewness actually, and the Gaussian assumption is not realistic in practice. As you can see in this histogram graph in the middle, we visualize actual sales distribution from one SKU. And you can see that the distribution has some positive skewness. It has non-tail on the right-hand side. If we hold normal Gaussian distribution as assumption, we can see the green dot here. It tends to overstock in practice. The actual 90% quantile is marked by the yellow dot. It's much less than the green dot. Therefore, we developed the quantile-based methodology and used the so-called light GBM method to calculate those inventory positions. As we can see, the numerical simulation results, which compare the two strategies, the new strategy actually not only reduced the inventory size by about 9%, it also the firms can enjoy a better out-of-stock performance rate. The out-of-stock performance rate actually has been reduced by about 3%. Furthermore, during those market fluctuations, the system can adapt quickly, especially like the periods during the June 19th to October 2019, as well as the pandemic. The next page shows the model details of this planning. First of all, we need to optimize with multiple objectives, such as transportation cost, the out-of-stock risk, the overstock risk, etc. And we need to take multiple constraints into consideration. For example, in D-2, we need to consider the the inventory positions, the brewery constraints, the DC constraints, the transportation capacity, and other business constraints. And in day-1, we need to further consider the shipping constraints and stakeholders' feedback. Overall, this is a quite large size problem with about 100,000 constraints and variables, and we need to solve within 10 minutes. And during the pandemic, as well as those abnormal events, a great challenge is caused by the shift of the distribution network. The distribution centers are sometimes closed to save costs and sometimes opened to gain better service rates. And the demands are shifted from one distribution center to another, which further impacted the demand within those DCs. We have to know that the demand from a certain region is actually affected by which DC is in charge of the service in this region. After the DC movement function has been applied, we can see that the forecasting error has been greatly reduced from 0.45, this is the mean absolute error, to 0.338. On the next page, we would like to highlight how we use the so-called big number method to improve the forecasting accuracy in those special days, especially during the pandemic. Actually, when we plot the sales, we can see that there are many peaks and troughs. Those peaks and troughs are often caused by those special events or special days. The normal forecasting methods does not perform very well during these days. However, we noticed one thing, that the sales team performs very well on the total number, which they call the big number, which is a national level forecast of the total demand. This is due to their experience, their understanding of the market, and the understanding of those information which has not been captured by the system. Therefore, we incorporate the big number trend into our machine learning model in order to improve the forecasting accuracy in those special days. We combine these two methods to achieve a much better forecasting rate. First of all, we use detection algorithms to analyze the big number trend and to mark the peaks and troughs in advance, and then put these categorical features into our machine learning model. Secondly, we use the posterior modifying technology to make corrections on those potential abnormal days, learning from the trends of the big number. For using these two methods, we improve the accuracy on those regular special days by about 2%.
Simai, we are,
yes?
are almost at the top of the 30 minutes. Do you think you could wrap up in the next minute or so?
Yes, sure.
Okay.
First of all, the daily model performed very well, and we can see that this model actually responded quickly to the fluctuations. On the left-hand side, we can see that this forecasting is much more accurate than the normal forecasting method. And also during the pandemic, it recovered quickly, which is marked on the right-hand side. Furthermore, after we implement the system, started from the end of March 2020, we can see the out-of-stock rate has been improved by 46%. And also, the misallocation cost has been decreased by more than 15%. Our planning time has been reduced from 4 hours to 15 minutes, and the information collection process has been greatly shortened. And also, we can see that when we consider the abnormal events, the performance actually has been even greater. Thank you.
Great, thanks so much, Simai. Very interesting presentation, super relevant, and it's very interesting to see that there's a lot of really interesting techniques that have helped us adapt to the pandemic. So unfortunately, we've used up all the 30 minutes, so we won't have a question and answer period for you, but we'll move on to the next speaker so that we can get everyone in. Thanks so much, Simai, for giving that really interesting presentation. So our next speaker is Chantal Bisson-Kroll. She is a director of machine learning at Kinaxis, where she leads the development of multiple intelligence solutions for the enterprise supply chains. Previously, she worked at companies such as BlackBerry, Bell Northern Research, Nortel, and Ericsson. Chantal is going to be presenting application of a technique in machine learning called AUTOML that's rapidly gaining popularity across the industry, and talk about some applications that we have at Kinaxis. So please welcome Chantal.
Thank you very much for the introduction and for the invitation to participate in this event. So the eternal question, what's the difference between machine learning and AI? They say if it's written in Python, it's probably machine learning. And if it's in PowerPoint, it's probably AI. What I have for you today is PowerPoint. But all joking aside, at Kinaxis, we write a lot of code and train a lot of machine learning models. All right. So today we'll talk about the use of AUTOML in our product, Rapid Response at Kinaxis, and go over some of the...
Chantal, you're not in full screen.
I'm not in full screen. I'm sorry.
If you maybe click the swap displays on the top of your screen, or I think it might do the right thing. Like in the PowerPoint preview, it's kind of showing the PowerPoint preview, maybe on your second monitor instead of the full screen.
Oh. How's that?
I guess it's still showing the PowerPoint preview for me. If you click swap displays in the top of the PowerPoint preview, it might, if you see the, worst case, maybe you can just not put it full screen. Oh.
Is it working now?
Much better. Yeah, much better.
All right. Sorry about these technical glitches. We thought we had that sorted out. Wonderful. So Kinaxis is a global company that provides a product called Rapid Response that is used by our customers to plan their supply chain. As you can see, we serve customers in a lot of different industry verticals, And as we're going to talk a lot about data today, you can imagine that the data that is relevant in, for example, automotive versus life science or somebody making electronic components can be quite different from one company to another. The supply chain planning steps that the product allows the customers to do include integrated business planning, supply planning, demand planning, inventory management, and command and control center. Today, we're going to focus on the demand planning portion of what the product does with machine learning. So this is an example of the type of data that is used in a typical supply chain planning system. Everyone is familiar with data such as order history or shipment history, and at different stages of the supply chain, different data is generated and stored. This data can then be used to inform the forecasts for planning the demand. Everyone is looking for improved forecast accuracy or the best forecast accuracy possible. Why is that? Well, very simply, to save money, to deliver goods on time, to avoid waste, and to avoid shelves being empty, as we've seen a lot within the COVID period. So beyond shipment and order history, a lot of additional data exists that can sometimes be used in different industries to paint a more complete picture of what drives demand and therefore be used to drive or to improve forecast accuracy. Knowing how to integrate this data into a planning system can be quite challenging and time-consuming, but if it's done well, it can be very profitable. Here are some examples of additional data sources that examples of them that can be used to further inform the demand forecast. So we have weather, things like events beyond holidays. Sometimes there are, festivals or store closures, various things. Web traffic, whether it belongs to a particular company or is more general. Sentiment data, social media data, search trends, market share, macroeconomic. If you're in life sciences, potentially epidemiology. And some of these sources of data are new and original. For example, they are trying to detect the rates of COVID by inspecting wastewater, and there's data for that. So it's quite a long tail of signals that actually can be considered to help improve and inform demand forecasts. So Kinaxis AUTOML. What do we mean by that? So the demand sensing application in rapid response is a system that takes one of the main signals, the one that we want to forecast. That could be your point of sale, for example, or your shipment data. And it allows you to add a number of additional signals that could potentially be causals that might be impacting this demand. The system, rapid response, takes in data from a lot of external sources, and on an ongoing basis, this data can be integrated through the system, through the integration layer. The AUTOML platform serves in the background to process this data, generate forecasts, and publish them in the rapid response application for the end user, in this case, the business planner, to use. So what do we mean by AUTOML? AUTOML is an automated machine learning workflow that is run end-to-end on the latest available data to generate a forecast. Let's look at this in more detail. So the first step, of course, is to ingest the available data. In this case, the first step is to ingest the data that's available for that specific company. So point of sale data, inventory data, potentially promotions, if that's applicable, but also data that might be relevant in terms of the specific competitors for that company. Potentially website data, for example, in the auto industry, if your users or customers are building virtual cars on your website before they actually purchase them, this kind of data could potentially be useful to inform the demand. And of course, social media, which can take a lot of different forms. Once the company data is available, another source of data can be external data, also known as public data. This is usually provided by various service providers. Examples of that would be weather data, financial indices. And what Kinaxis does, because it's quite consuming sometimes to prepare all of this data and augment your data set that is company specific with this additional data, what we do is we have prepared ahead of time the ability to add this data and exposed it in the form of a catalog that can simply be selected. The system is smart enough to use the location and time frame information from the company data to go fetch the relevant data for, weather or indices that have been selected by the user to augment their data set. Once we have all this data, we need to harmonize it, clean it up, and transform it. So as you know, machine learning models cannot use raw data in its raw form. So there's a number of steps that are taken to make the data more meaningful to the machine learning models so that they can actually get meaning from it. An example of transformations might be to take a date, which is a string, and actually split it into year, month, and day. If there's an event such as, I don't know, Mother's Day, sometimes it's more useful for the model to know how many days away from Mother's Day today is, rather than is today Mother's Day or not. So this step is probably one of the most important step of the whole process to get some good results with machine learning. Once we've generated all these features, we've taken all this data and turned it into a number of features, the system needs to select which ones are actually most likely to be predictive and better inform the forecast to improve the accuracy. Once the most important features are selected, and we use different techniques for that, it's time to actually train some machine learning models and select the one or the combination of models that produce the best KPIs. Now, all of this, as is, would be a black box. And with machine learning, it can be tricky because the model may infer some things from the data that may be extremely insightful, but could also be potentially incorrect because it doesn't know the domain knowledge in detail. So what we add to this is an explanation of the result. So the forecasts are generated with explainability, and this takes the form of diagrams that show things like the future contributions, and these can be local or global explanations. So adding a data source, when we find ourselves in situations with a lot of uncertainty, like COVID times, sometimes what we want to do is add a data source relatively quickly. And we want to be able to do that without having to change the software. So to enable shorter time to value in adding such a new data source, AUTOML in itself is not enough. So we've complemented it with a couple of key techniques. The first one is that data is ingested into the system using a self-described schema that is combined with metadata, which informs the feature engineering. and the intelligent data fusion, which we're going to see on the next slide. This can be combined with discovery tools that allow the system to be used to iterate through a number of possibilities and find out things like at what aggregation level a particular data signal should be used. In particular, if this particular signal happens to be quite sparse in terms of the number of data points in it. Sometimes it's best to aggregate it a certain way before ingesting it into the system. So what do we mean by data fusion? If you have some of your data at the product level, for example, with some location and at a monthly frequency, this could be sales data, for example, and you want to mix that with a financial index that is relevant to a particular sector of the industry that is published on a daily basis, together with sentiment data that potentially at the brand level that you might be acquiring on a weekly basis, and then weather data that is available on a daily basis. When you want to mix all of that together, what the system does is what we call data fusion, and it will create a unified feature representation that it will then pass to the rest of the feature engineering steps in the AUTOML framework. So when adding a new signal, it will simply add one more here and create a new unified feature representation and pass that on the next time we want to forecast. This is what an example of explainability looks like in the product. So in the context of a demand planning screen, there are specific forecasts on certain dates, and by clicking on them, it opens up a diagram that shows some of the feature contributions that push the forecast upwards, as well as some of the feature contributions that push the forecast downwards. And one thing to keep in mind, though, is that this should be really used as correlation and not causation. But still, it really informs the user as to what it opens a window as to what the model actually picked up as important features for this particular forecast. And should anything look a little out of place out of these explanations, it allows the data scientist and the specialist with the domain knowledge to circle back to the way that the data is configured for the system to generate results. Okay, so let's go over a few use cases where we've applied these techniques in different industries and what results we saw with the use of AUTOML and the addition of less traditional sources of data. So the first one is a consumer electronics company. And in this case, this company actually acquires sentiment data in the form of sentiment scores. So when we talk about sentiment data, we're not talking about text. The text was converted by this service provider into actual numbers between 0 and 1 that reflect whether the sentiment about a particular product or group of products or a particular brand are positive, negative, or neutral. We used this type of data. I believe that the provider here was Sprinkler, which offers this kind of social listening service. And we used this kind of data and got some actual good results in terms of adding the sentiment to the base forecast. This is an example of the addition of sentiment data to one of their high-selling items. You can see in green the base forecast that we had without using sentiment data. And in orange, the addition of the sentiment data brought the forecast much, much closer to this peak, which happened to be related to the beginning of the COVID-19 period. One thing to keep in mind with these kinds of signals, sentiment and social media related, is that we tend to use them with a lag. And what I mean by that is that when somebody expresses a sentiment online, the effect of that can last for some time. So for example, if somebody puts a review for a product on Amazon, that review might still be read, a month, 2 months later easily. So it's not attached exactly to the day when it was published. For this particular company, we saw that the addition of this social sentiment data improved the forecast accuracy in 81% of the forecast periods that we tested. And in the brick and mortar stores, it improved the forecast accuracy by 25%, and for online stores by 11%. Our next use case is in the consumer cosmetic area. In this case here, we were working with point of sale data, and this particular customer is integrated into social media. So for example, at one of their flagship stores, they have a booth where they encourage their customers to post something on Instagram using their products. So what we did is we set up social media information that was rooted in counts of posts and counts of likes on this on these particular sites. These statistics were ingested as a signal, and similarly on Reddit, there were industry-related groups that are very, very busy discussing these products as well as the competitor products. And we use the social posts, the counts of social posts and the counts of likes of this type of data, and mix that, of course, with the historical time series to inform the forecast. What we saw with the addition of this data was a 6% increase in forecast accuracy by adding these social media data signals, and a 45% reduction in bias. So bias is really, of course, in this case, did we over forecast? Did we under forecast? We want that to be as close to zero as possible. So a 45% reduction was an excellent result. Our last use case is a food company. So here we were forecasting what the demand for a particular food product at a particular store. This was in South Korea. We used a broad range of signals here. We used, for example, search results or search trends from a search engine combined with weather, various events. In that country, there are mandated store closures every second Sunday. And having this data made a big difference in informing the forecast. So in a supply chain plan for this customer, using a mix of these data signals for 55 products at 140 stores, what we saw was the ability, the forecast was so much more accurate that it was possible to reduce the number of days of stockouts when there was nothing left on the shelf by a full 60%. And this was actually accomplished while requiring 7% less inventory and therefore reducing costs for this company. So today we went over how machine learning is used by our Kinaxis rapid response products, and some of the methods that we use to take advantage of data signals that were not typical, and some of the successes that we've had in use case studies to improve forecast accuracy using these techniques. Thank you very much.
Great, thanks so much, Chantal. Really interesting use of especially these data signals that are hyper relevant when new things happen, which they almost always do. So we actually have a few questions. I just want to remind everyone, you can actually post it if you're on Zoom in the Q&A section, or if you're on YouTube Live, you can also type in the comment box and we'll pick those up as well. Okay, as well as if you're on Zoom, you can actually vote questions up and so that, we can try to get the most popular ones as well. So Chantal, we have a question from Elaine. How much do you use explainability component of AutoML in your projects? How does it provide value? Thanks.
How does explainability provide value?
Yeah.
Okay, so well, first of all, it can surface some insights. So as an example, what we found when using social media data is that certain social media influencers, for example, actually had quite an impact when they blogged about something and they had, thousands of likes. This actually was picked up by the model as an actual important predictor. And it's not something that would be easy to know if you just used AutoML in a black box fashion. You would only get a potentially better result, but you wouldn't know why. And you certainly wouldn't know that this particular influencer on social media is actually making a difference in how your consumers are behaving. Similarly, you can find out that there is information about your competitors that's actually showing up and bringing down your forecast that gets picked up by the model. Very importantly, if a model has done something wrong, found some kind of correlation in the overall data with something that happens to be a complete fluke, this would also be surfaced in the interpretability and could therefore be corrected, could be seen and corrected so that it's not used incorrectly.
Great. So Cameron also has a question here. How can data be interpreted to allow for differences in patterns or simply a lack of data, for example, in rural versus urban areas?
I don't think interpretability, the way that I described it, would address that. If a lack of data would often translate into a feature not being very useful and being excluded at feature selection time.
Okay, great. And then Ryan has a question here. Is there a risk of sentiment overweighting relative to the baseline trends? A small subset of the population tends to be more vocal, and their distribution may not always map to overall customers. So how was this accounted for?
That's a great question. I think one of the things that's important in a system like this is to allow various configurations, to allow the user with the business knowledge or the data scientist with the domain knowledge to be able to put weights on certain signals. So you may want to ingest sentiment data, but you may want to actually configure it to be weighted in such a way that it cannot overtake the whole thing.
Great. That makes a lot of sense. And Cameron has another question here. To what degree can sentiment tracking be used to develop a metric to measure the effectiveness of advertising expenditures?
I need to think about this one for a minute. Advertising expenditure. So I assume that one of the signals could simply be that. A data signal that describes the advertising expenditure. And if it's predictive, it would actually be picked up by the model and show up in the explanations.
Yeah, that makes a lot of sense. Because I assume that a lot of companies probably are spending, part of their marketing budget on social nowadays. And so they're probably correlated at least. Okay, so forgive me if I'm pronouncing this name wrong. Rashab has a question. Has AutoML helped in predicting demand or improving forecast accuracy for a generics pharmaceutical manufacturer?
We have not used it for in the life science pharmaceutical yet.
Okay, but I guess there's no reason why we couldn't use some of this technology for that.
Absolutely. Yes, there is nothing that would prevent that use.
Great. Next question. Forgive me if I'm pronouncing this wrong. CV. They're wondering what is under the hood. Python. What models?
Oh, under the hood, LGBM. Of course, the AUTOML can actually train a lot of different models and tune them. The hyperparameter tuning is also automated. But in the context of demand forecasting, LGBM is one of the usual winners.
Good. Yeah, for those who are more technically minded, I'm sure that makes a lot of sense. Okay, and again, a name I'm not familiar with. Shrikanta has a question. Has Kinaxis been applied to retailers with millions of item location combinations?
So we are in the process of going into the retail industry. We have not applied AUTOML at retail scale yet. This is something that's on our roadmap.
Yeah, and so you should definitely keep following Kinaxis because there's going to be some interesting stuff coming down the road. Okay, and let's see who else. Okay, Rohit has a question. How much data did you use for the models? Several months, quarters, years, etc.?
Oh, typically 2-3 years, although with COVID that has proved to be quite challenging as history is not always a good predictor anymore, but generally 2 to 3 years.
Okay, good. And then Elaine has another question. Have you ever used or applied optical document processing into AUTOML for any of your projects? Thanks.
Optical document processing, no. Currently, everything is number-based, not text-based. So, no, we have not yet.
Okay, great. So we have a couple of more minutes. If any one of you have any more questions, oh, actually, Elaine has another question. Do you have any suggestions on how to deal with the effect of COVID on history and processing?
I think that's a bigger question than I can answer in a minute.
Yeah, I feel like just speaking from some of our experiences, Chantal, I think a lot of people are learning how to deal with this. And I think a lot of techniques are just emerging in the past year of what the best way to deal with it. So might be an interesting topic for another event, I'm sure.
I think the comment I would make there is that it's important to consider something like AUTOML as something that's in partnership with the humans that actually have the business knowledge, the intricate knowledge of the data. It's intended to make their work easier, but not to replace it.
Very good point. Very good point. Okay, and then I guess Mariam has a very similar question, but well, maybe we can elaborate a little bit more. How did you adopt the machine learning models to work for COVID times as well?
Yeah, I don't, it's essentially all driven from the data that we feed it as opposed to changing the models, so.
Yeah, and if maybe I could just add something is that I think the data point is very important because at the end of the day, the machine learning is a technology, right? Or like it doesn't really know the situation. It only knows it to the extent the data is input. So if you don't have the right data or you're not adding in, for example, things related to the changing environment of COVID, you probably won't get the right output.
Well
all
said.
right. So I guess we just have a minute left. So maybe Chantal asks you another question is what other areas besides forecasting do you see AUTOML being applicable in the supply chain?
Oh, sure. So at Kinaxis, we have another application called self-healing, which also uses AUTOML. The focus of that application is to monitor and correct the master data that's used in a supply chain plan. So for example, if you have lead times that are captured for all your products in your supply chain, AUTOML is used to forecast what your lead times should be based on historical information and highlight to the user which lead times are out of whack and either autocorrect them or put them up for the user to review and adjust accordingly.
Great. Thanks so much, Chantal. Very interesting, especially the use cases, I think, of applying this technology. Great.
Thank you very much.
Thanks, Chantal. I'd like to welcome our next speaker, Sinem Keng. She is a PhD candidate in operations management and statistics right here at Rotman. Her research focuses on e-commerce fulfillment decisions using large-scale data sets. So today she's going to present some of that research. And given the huge rise in online shopping due to the pandemic, it's a very, very relevant topic. So Sinem, if you're there, please welcome Sinem.
Yep. Thank you, Brian, for the introduction. And I'm really excited to be a part of this event. And so the work that I'm going to be talking about today is called Store Sequencing for Online Order Fulfillment Problem. And this is a joint work with two of my professors who are also in Rotman, Ofer Baron and Andres Sire. So in order to motivate my work, as the title suggests, we're dealing with an online order fulfillment problem, and this order can arise anywhere within the country. And these orders are primarily can be shipped from the distribution centers or from the brick and mortar stores throughout Canada. And essentially, the distribution center is the cheapest and fastest option to satisfy these online order fulfillment online orders. However, we can use stores if we have to. So in Canada, the Canada Post actually categorizes shipments as into three. First one would be a local shipment if the origin and destination are located in the same city. And they are called regional when these 2 points are within the same region. And this region definition also comes from Canada Post. So to give you an example, for instance, for Toronto, the regional shipments would be from anywhere in Ontario or Quebec. And finally, any other shipment would be categorized as national. So if we denote the costs of these shipments as C local, C regional, and C national, we have the relationship as local is always cheaper and faster than regional, as well as it is faster and cheaper than national. And also, we have this relationship where shipping everything in a single package, even though it is from farthest place, a national shipment, is still better than shipping this order with 2 packages from a local place. So we prioritize shipping everything in a single package. And in this study, we're working with one of the largest retailers in Canada. We have their data, and we try to use their data to have better fulfillment decisions. And our objectives are to have less delay to reach to the end customer as soon as possible, and also with the lower transportation costs. And these two objectives are aligning with each other, and therefore we focus on them together. So if I have to describe what's happening currently over this simple flow chart, an online order arrives to the system and the distribution center is first checked. And if everything goes wrong, if there's enough inventory, if everything goes well, and if there's enough inventory, then this order is shipped to the customer. Otherwise, we start checking the stores, and there are certain criteria to do so. But once we find a good store, then a request is placed to this place. So at this point, this is a decentralized system. This store has a decision to make. It can either accept this order and ship it to the end customer, or it might say, I'm not going to do this, so reject this order. So you have to go to find the next store until you ship everything to the customer. So possible reasons to reject an order would be either low inventory levels. So essentially, when you're checking and deciding a store, you would like to pick the ones that have enough inventory, but still the demand of the brick and mortar store might be high, in a sense that they want to prioritize their walk-in customers so that they reserve these low inventories to these people instead of satisfying an online order. And also there might be staff shortages because this process is an extra workload which requires labeling and packing and shipping. So there might not be enough manpower to do so. And then the store can reject an online order. So in this work, we're focusing on the store sequencing aspect, and we would like to come up with stores that would reject less so that you can reach to the end customer faster. And also we would like to do it in the least costly way. And as I mentioned, we have data, and this data covers 2 years of 2019 and 2018 and 19. And the company has a single distribution center, which is mainly allocated to online order fulfillment and about 100 stores throughout Canada. The main data that we have is the e-commerce order transactions. So on an order level, we have the idea of an order, items, IDs and quantities, and when the customer placed this order, as well as the customer location in terms of their zip code. And in terms of fulfillment, we have the stores that accepted the items and when they shipped it to the customer. And we can also track the stores that rejected these items up until they are shipped from somewhere. And finally, we have weekly inventory and sales data of every store at SKU level. So we are focusing on the orders that are shipped from a store because we are dealing with store sequencing problem. And this results in about 2 million single item orders and 1.2 million multi-item orders. And an interesting fact is that 45% of the multiple item orders have only 2 items in an order. And this is a fact that I'm going to use in a bit. And just to give you an idea of the sales volumes from a store for online orders, on average, a store ships about 32,000 orders per year, and the major stores can have more than 100,000 online orders annually. So as I mentioned that stores can reject some orders, and at this point one might wonder whether these rates are high enough or how they affect the problem. So we drew the charts of rejections at the top 3 stores of the company over the 52 weeks of a year. And what we observed is that at the beginning, there is almost no rejection for a while, and then it slightly increases. And mostly within the last 4 months of a fiscal year, we see high rejection rates. And this is the time that coincides with Black Friday and Christmas. So this is the holiday season where the demand is also higher compared to the normal times. And if we look at the average rejection rates over all stores, we see up to 20 to 30% rejection rates during this season. And this aligns with our expectations because, as I mentioned, as the demand is higher, these stores want to reserve their items for the walk-in customers because they know that they are going to be able to sell them. And as the business increases, the staff won't be available for the online order shipment. If we look at, I mentioned that the shipments are categorized as local, regional, and national. And if we look at the distributions of them in 2018 and 19, we see that about 10% of the shipments are local, and like 56 to 59% of them regional, and let's say 32% of them are national shipments. And finally, we look at the multiple item orders to understand how often we see split deliveries. So on average, we can say that 60% of the time, the multiple item orders are shipped within a single package, whereas the remaining 40% of the time, we see multiple shipments. And if we just focus on the 2 item orders, so there's a definition that we came up as necessary and unnecessary split. So Let's assume 2 item orders that are shipped from 2 different stores. So each store ships one of the items, and we look at these 2 stores. And if neither of these 2 stores has both of the items in inventory, we say that, okay, there was no chance that you would be able to ship these from a single store, so this was a necessary split. However, if at least one of these 2 stores have both of the items in inventory, this could have been avoided. So we call this as an unnecessary split. And if we look at the distributions, we see for only 2 item orders, 48% of them are shipped in a single package, and 15% was a necessary split, whereas there's a 37% rate that we have unnecessary splits in the orders. So our objectives based on this descriptive analysis is to have more local or regional shipments and less national shipments to decrease the rate of these. And for the multiple item orders, we would like to decrease the number of split delivery rates, especially the unnecessary ones. We would like to avoid those. And considering the rejection rates, we divide this problem into 4 sub-problems, as in single and multi-item orders, and where we focus on first 8 months, assuming there is no rejection, and the last 4 months, where the rejection rates are, as you have seen, 20% rate on average. So we have a mathematical model to model this problem, and dynamic programming. You can see the elements that we have here. We keep track of the set of stores that are available, and we have number of items in an order. And a store has a probability of accepting an item with PI, store I has PI, and QI would be the rejection rate of a store. Then CIs would be the transportation cost from each store. And we would like to find the minimum cost when you have K items to be shipped from an available set of stores N. And our model would look something like this. So we, for each J, where J is the number of items rejected, and we multiply the probability of rejecting J items, and we pay a cost of CI if at least one of the items in an order is accepted. So if there is a package going out of the store, we pay the cost of CI, and then we move on to the same problems, the same structured problem, but with less items, now J items to be shipped, and we remove that store I that we already asked from our available set. And for each item that we won't be able to ship to the end customer, we are paying a huge penalty cost. So the results tell us for single item orders, the optimal store sequence would be just starting from the cheapest store and moving towards the most expensive one. And that is a nice result that can be applied. But for multi-item orders, we have proven that this is a hard problem to solve. So for those of you who are familiar, it's an NP hard problem. And so there basically is no simple algorithm which would solve this problem to optimality. That's why we came up with possible algorithms for the only 2 item orders. And as I mentioned, 45% of the items, multiple item orders, has 2 items in it. Therefore, we decided to focus only on them. So the first possible algorithm is myopic policy. As if this is a single item order, we order the stores according to their cost and start from the cheapest one. And then we have what we call as an advanced algorithm. This relies on the 2 store optimality conditions. So we solve the 2 store problem to optimality, found the conditions that make them optimal, and then use them for the n store problems. So if we look at some results from a myopic policy, we showed that this policy would be optimal if the acceptance probabilities are high enough. So for those of you who are interested, this is the expression, what high enough means. But if I illustrate it with a simple example, so if we assume 4 stores, let's say with transportation cost $6, $8, and $16, The myopic policy will be optimal when the first store has an acceptance rate of at least 86%, and second and third stores need to have at least 67% acceptance probability. And the intuition that we got from here is that when the gap between two consecutive cost values is larger, the myopic policy will become more likely to be optimal. So here, for instance, the rate between the consecutive cost values is 1.33, and this resulted in 86%. But when the ratio of two costs become 2, as in say 8 and 16 here, the ratio becomes 67. So this ratio decreases, and that means you have more room to be optimal with the myopic policy. Okay, so we have some conditions where it's going to be optimal, but what about its worst case? And we have shown that for 2 item orders, the worst case would be as 2n, where the n was the number of stores, minus 1 over n times the optimal. So the intuition is that as the number of stores increase, the worst case cost becomes twice the optimal. And most of the times it is performing much better than that. And we don't have data results for this, but theoretically we have also proved for m item orders and generalized this solution. We can show that the worst case cost becomes m times the optimal, and this is independent of the cost values. So yeah, this is the end result that we got, and it performs most of the time much better than these worst case. And if you look at the advanced algorithm that we developed, is we use the optimality condition for the 2-store problem, which is the expression denoted here. So how it works is we first, based on the customer location, we categorize the stores as local, regional, and national into 3, and pick the best ones out of these 3 regions. And then when we end up with 3 stores, we make pairwise comparisons using this optimality condition that we have and select the best store out of these 3. And then we place a request to the store. And if it accepts both of the items, this would end up with a single shipment. And if the store accepts only one of the items, now you have only one item remaining to satisfy. So we know this is a single item problem, and we have known that myopic policy is optimal for them. So we just apply it here. And let's say the store rejected both of the items. So and assume this was a regional store. So what we do, and we come back here and find the second best regional, but keep the best local and national stores. So we move on to making another 3 pairwise comparisons to find the best store and so on. So we keep this loop until every item or both items in the order are shipped to the end customer. So some results on data is we applied the algorithms using these available data for 2 years to see their performance. And we only focused on single and 2 item orders, and this would result with 2.5 million orders per year approximately. And some assumptions that we have is that, as I mentioned, all local stores have the same cost, like all regional stores have the same cost, and as well as for the national ones, so that within a region, the stores are not different than each other in terms of the cost values. And while testing our algorithms, we use the real acceptance probabilities that happened that day. In reality, we don't know them in advance, but we use them for testing purposes. And the inventory levels are taken from the previous Saturday. So we have weekly data on inventory. Therefore, we rely on the previous week's inventory to make decisions here. So if we look at the percentage improvements, and these are a little bit on the optimistic side, but we don't see that much of an improvement for the single item orders, between 3 to 8%. There's a range, but where the main gain lies for the multiple item orders. So we see with a combination of and some changing some parameters, we can see about 20 to 25% improvements for the multiple item orders. And if you recall, the rate of single shipments was 60% and multiple shipments were 40%. And we can decrease that 40% to 28 with these algorithms. And some other opportunities that are not covered here is that, as I mentioned, we're using the real rejection probabilities that happen that day, but in reality, we don't know in advance. So there needs to be a prediction model going here to find good estimates of the rejection probabilities to make use of the algorithms. And also we are currently looking for some pilot implementations with the company and to get some results there. So that would be all. Thank you for listening, and I'm happy to get some questions.
Great, thanks so much, Sinem. They're definitely an interesting problem and something maybe we don't think about so much when we're just randomly putting new items in our basket and asking the companies to ship to us. Yeah. So just as a reminder to the audience, you can actually ask questions in the Q&A box in Zoom. And then if you're on YouTube Live, I think there should be a comment box where you can do that. So let's get started on the first question. Anne has a question. Is local versus national fulfillment dependent on the type of the product? For example, I guess a hardware item like from Home Depot versus maybe a piece of clothing.
No, it actually only depends on the distance where you're located in the city. So every item in this setting as viewed as the same item. So we don't differentiate on items, and it only is dependent on the destination.
Okay, interesting. So I have a few questions that maybe I can ask while we see if anyone else from the audience has some more. So what are some typical reasons why the distribution center can't fulfill the demand for online orders? Because you mentioned that it was a lot cheaper to ship from the distribution center versus the stores.
Yeah, the main reason would be just a lack of inventory. If there is not enough inventory there, you might want to use your stores. And the second thing is that, as I mentioned, single packages are always prioritized over multiple shipments. So if you are not able to ship everything from the distribution center, and if there's a store that can do it, you might still prefer a single shipment over the distribution center. So that's another reason. And also at some levels, so since there is a single distribution center and some customers might be really far away, and maybe there's a closer store, and you might want to reserve your inventory levels at the distribution center for the customers that are actually closer, and you would want to use stores inventory for the farther away one. So these are some possibilities why.
Yeah, and it sounds like maybe an opportunity to do more complicated research with all of those different constraints involved. Yeah. Interesting. Okay, so we have another question from the audience. Prazen, if I'm pronouncing that correctly. Is very happy to learn from your the study that you did. So a short question would be, what are the computation requirements required to implement the solution? How computationally intensive was it?
Which one? I didn't get. How the computation intensive was?
Was the algorithm that you ran?
I mean, we call it advanced algorithm, but computationally it's not that advanced, as I would say. Just to give an idea how long it takes, and for this size of a problem with about 2.5 million orders, it takes about 6 hours to get results from the algorithm. And yeah, that's
so if because this was a Canadian national retailer, say if it was a US national retailer, maybe 10 times the data size, would you expect it just to be 60 hours?
60 hours? Yeah, I think that would linearly increase with the order size. Yeah.
Okay, interesting. Okay, so maybe I'll ask another question. What do you expect the performance of your algorithm to be if you relax some of the assumptions you talked about earlier, or maybe modify them somehow?
Yeah. So yeah, as I mentioned, we're using the real rejection probabilities, and estimating them would bring some error to the table instead of knowing them in advance. So we expect to see a decrease in the percentages improvements that we have once you have some estimations. And also, as I mentioned, you're relying on the last Saturday's inventory levels for a Friday order as well. So maybe that inventory level would already be gone until Friday, but you assume it's still there and make decisions based on that. So that would also, if you have more accurate inventory data that you can keep track of, that would also decrease the percentages of the improvements that we expect to see. Yeah.
Yeah, I guess like once you actually include a lot of the realities of the situation,
yeah,
it's
exactly.
not as ideal as maybe some of the simulations that you've done.
Yeah,
makes a lot of sense. So another question I might have is that this is maybe a national Canadian retailer. They probably don't have their own team of PhDs, and maybe a lot of other retailers are similar. So what is the prevalence of some of these advanced algorithms in the industry, like based on your knowledge, and how many of them are using things like this versus maybe it's just a simple policy of the closest store or whatnot?
Yeah, as you said, I believe I'm not that knowledgeable on the industry aspect of it, but as you said, starting from closest store and moving towards the farthest or most expensive one is sensible thing to do, and I believe most of the companies are trying to do that because it's simple and intuitive, right? And our results suggest that at least under these circumstances, it's not a very bad idea. And so it's easy to implement and intuitive, and it can be optimal under certain cases. Therefore, I believe a lot of the companies will be using them. Yeah.
Interesting. And I suppose it probably only makes sense to start optimizing some of this stuff once you get to a certain scale, right? Yeah. Because as you mentioned, the two item or multi-item order problem is actually where I guess a lot of the suboptimality actually happens.
Exactly. Yeah, because then if you're prioritizing single package to multiple packages, maybe the closest one is not always the best one. So it brings some complexity to the table.
Interesting. And so I guess following along that question, you were working with a Canadian retailer. I imagine that's a good thing for both parties, right? The retailer is getting some benefit of solving this kind of high value problem, and you're able to actually get real data to do your research. Yeah. So maybe you can talk a little bit about that relationship, how it was established, and maybe even some of the people on the call would be interested in partnering with you or some of the other faculty at Rotman.
Yeah. So it's actually a very mutually beneficial experience for us, I believe. And I had the chance to work with data earlier on in my education. And the relationship was actually established by one of my prof's advisors, Offer Baron. So I believe they have already done a project earlier, so they were familiar with each other. And when this opportunity was there, I had the chance to be included in it. But yeah, I believe if it's possible to do so, I think it's a valuable experience.
Interesting. And were there any challenges with access to the data and making sure things were kept private? Because
actually that process naturally took some time. There were some changes because of the security issues and having a virtual desktop for only these purposes and so on. But overall, I think it went smoothly than most of the other experiences that I heard about.
Well, that's good. And so if anyone's on the call who's interested in having some smart folks from Rotman working, I'm sure a lot of the professors are very eager to get their hands on data, especially solving these types of different optimization problems and which occur very frequently, especially in the supply chain.
Yes, we are eager. Yeah, I believe so too.
Okay, thank you so much, Sinem. That was a great talk and a very interesting discussion with you.
Yeah, thank you.
Okay, so I would like to introduce our next speaker, Mani Janakiram. So he's the last speaker, but last but not least, he is a senior director of data analytics at Intel. And with over 21 years of experience at Intel, he's worked across many different strategic projects, such as factory operations, capacity planning, supply chain, and analytics, just to name a few. There's many, many more. He's also an adjunct professor at Arizona State University with a PhD from Arizona State and an MBA from the Thunderbird School of Global Management. Manny's going to talk to us today about how Intel has been leveraging AI and analytics to build intelligent and autonomous digital supply chains. So please welcome Manny.
Thanks, Brian. Good morning to all. Let me go ahead and share my screen. So let me know if you can all see my screen.
Yep, we can see your PowerPoint. And
perfect. I'll go full screen.
Yep.
And so jumping into the topic, the first slide I wanted to kind of bring in here is the entire world is becoming digital. I think all of us are aware of that, and it is even more paramount during the COVID times. We never imagined the AR and the VR and the application of connected devices and connectivity would, in fact, like in the academia also, we feel that, right? Everything virtual and things like that. Imagine the compute power needed to make it all happen, right? So the digitization is happening at a much rapid pace than what we thought would happen. And Intel is actually powering, like this kind of a growth as well, whether it is a cloud, whether it is connectivity, artificial intelligence, and intelligent edge. So I'm going to use a couple of slides to kind of bring to us, what we do, and then kind of connect to supply chain, and then kind of bring home the AI advantage in supply chain. And I'm sure most of you are familiar with the Intel, one of the world's largest semiconductor. We call as the, like the largest IDM, integrated device manufacturer, meaning we design to manufacture to deliver silicon and silicon-related solution at scale. And it is critical that what we do is, being trusted, and it also unleashes the potential of data. And we have a new CEO, Dan Gelsinger, and he primarily, has basically, like we are looking at what we call as the IDM 2.0 to become the leading provider of silicon globally, whether it is our own product, whether it is leveraging external foundries to make our product that the customer wants, or to even make product for others in the form of foundry. So that is where Intel is unleashing the potential in engineering the future, and primarily supply chain is going to play a very critical foundational role to this Intel success. And so having said supply chain, I just want to kind of give a quick view of what supply chain at Intel mean. Primarily, like it is not necessarily hundreds of thousands of SKUs, but it is the scale and the complexity that really matters for Intel supply chain. For example, Intel Fab is, like a fabrication facility. It could be anywhere between $4 to $6 billion. Our capital spends would be in the $15 billion range, and our total, like a spends that we manage is in the $35 billion in addition to the capex. And we have a worldwide, like a presence. And we have assembly manufacturing, wafer fabs around the world, warehouses, and around 1 million orders we process on a regular basis. So, 3,600 supply chain professionals, several of them technologists and PhDs. So it is quite a widespread. And in order to make our supply chain more capable to deliver value and solution, we have been leveraging the power of AI. And earlier, you heard from Chantal that, hey, what's the difference between AI and ML? And I think it's an interesting question, and I'm going to get to that. But before we even get there, what is actually driving this revolution? When you look at a few years ago, The technology was ramping up really fast, but the fusion of technology was not necessarily happening at the rate it's happening today. Whether it is in-process memory, whether it is ability to handle unstructured data or big data, whether it is able to get the various data streams through IoT and different like data collection mechanisms that are fully integrated, whether it is the computational power, or mainly whether it is ability to reason, meaning converting data to intelligence through the AI ML algorithms. When these are all maturing and when they come together, that is where the magic happens. And that is what we are actually seeing today. And in order to bring everything home, one of the things we're looking at really is what I've been calling as the autonomous digital supply chain. And primarily, what is autonomous digital supply chain? A lot of people ask, right? In the previous slide, I was showing integration and fusion of different technologies. And one example that you would actually leverage and experience is in the navigation system. For some of us who go back a few years ago, early 2000s, when we did not have necessarily a good, robust, like a Siri or, like a Google Maps, we were dependent on a paper map. I remember, going to a new place, renting a car and they would give, paper map, and I would open it up just like the guy out there and start to plan my travel. I'm going to go from point A to point B. And of course, with some mistakes and things like that, I end up going where I want to go. But today, we just punch the destination and voila, the navigation system with a very nice voice leads you to where you need to go. If there is traffic, it gives you direction. If you have to do some changes in the path, it gives you direction. If you make a mistake, it takes you back, right? So it is automated to get you to the destination. Imagine a few years from now, the way we are making progress with autonomous vehicles and with shared economy and everything, you don't have to really know where you are going because your vehicle is more like a data system on wheels, and it is integrated with your schedule, with your like all the other details, and you get in and it knows who you are, where you want to go. Voila, it takes you there. So that means we are making great progress from a manual to automated to autonomous. The question I kept asking a few years ago is, how do we make this capability applicable, available, and useful within the confines of manufacturing supply chain? And I started to look at, how the supply chain is kind of set up with the SCORE model. Like we have very clearly defined silos, like, plan, source, make, deliver, return, and our systems and tools and our, our enterprise solutions, and even our talent and folks are trained to be experts as a planner or a logistician or a procurement person, things like that. And systems were not necessarily integrated. So instead of having a very well-defined silo, we should start to look at an integrated, more like a matrixed supply chain. And that is one of the things that would enable us to get to autonomous digital supply chain. And the value, as I listed down there, are several, right? But again, what are the things that are required to make it happen, right? I mean, it's not just that you can, like one day you get up and say, I want to be, I want to have my supply chain to be autonomous. But it needs foundational work, meaning understanding the business processes, having the right data structure, connecting with the right intelligence, and then having good business processes, and then having the right culture and strategy to make it happen. All those things are critical. Having said that, now the question that I wanted to ask is, what's the difference between AI and ML? To me, AI is a methodology. It is a concept to create intelligent solutions that would leverage machine learning, that would leverage, business processes, RPA, and everything together to provide a near human or a human kind of an experience. Machine learning, I would call it as a subset within the AI that allows machine to, compute and come up with, learn from data to provide solution. With that in mind, I have a few examples. And, there are several of these instances that we have at Intel. We have implemented many of them. And I think our challenge really is to bring it all together, integrate it so that we get the value of 1 + 1 = 3. But what I'm sharing here is some, very useful examples that we have implemented. And I'm starting out with some of the methodologies and concepts, right? One is every one of us really want to understand how our system, how our network, supply network, or for that matter, factory is running. And so that once we know what is happening, then you can actually make improvements and you can even optimize it. So the virtual factory, supply network modeling, and then eventually a path towards digital twin is where a lot of our activities are involved. And here we're optimizing factory supply chain by integrating data, modeling and simulation. And once we have that kind of a network, we can actually improve our operational excellence. We can, like our capital expenses, and we also do a lot of scenario modeling in that space. The second one is we have, like thousands of products, and then we have very expensive factory network capital. So leveraging and having a better supply demand alignment and planning and scheduling is critical for us. You can imagine, like different combinations, different configurations that we have to really look at. So we have a huge planning engine and more like an optimizer. And here we actually integrated our solver optimizer with the AI solution, data science module, along with some of complex event processing and also robotic process automation to not only provide a prescription of what to run, where to run, how to run, also to explain why we are doing what we're doing with different scenarios, and in several cases to automate some of these processes and steps. So I'm going to get to that as well. And then we also looked at our supply, like our contracts. I think most of you are familiar with the procurement and contracts. You understand the trouble and the pain it takes to create, depending on the size of the project, whether it is a strategic or tactical, or whether it is a high value item. Contracts could be anywhere from 2 pages to hundreds of pages, and with a lot of details, and with subject matter experts, with legal, with finance, with supply chain folks all participating, right? So in this case, we wanted to look at how the contracts exist, what we can do about it. And one of the challenges we faced was the current contract with the existing enterprise system was very hard to actually pull out of to understand, okay, what is the indemnity factor? What is the warranty? How do they compare across contracts? Can I do some auditing? So what we did was we basically pulled those contracts. In some cases, we have to digitize them. And then through the application of natural language processing and RPA and machine learning, we were able to go from a, like a non-digital contract to a purely integrated, digitized, intelligent contract. And I think I'm going to share that as when we go into the next page. And the other one is the visibility, which is a #1 requirement across, any of the, whether it's a retail, whether it is a B2B, if you're moving something, you need to know what it is, the product or this, like the solution, and you need to understand what is going on with it. So in our case, we not only provided a visibility, we also wanted to add predictability. In the sense that we want to actually look at what's going to happen if I, for example, inventory, right? What's the days of inventory at different, like network levels, and when do I have to plan for safety stock, planning and order, and like things of that nature. I will share that as well, and connecting that with our entire visualization system. So that is another capability. And then, of course, the ecosystem sensing is critical for us overall, from managing the supplier connections, understanding risks, and primarily leveraging, we're also big on sustainability to ensure that the compliance across the board. And in this case, we leverage the cognitive AI ML with the natural language processing to pull data from web sources and things like that to make sense out of it. And it has been providing a lot of value, and we're also being recognized across the industry for the work we're doing. And now kind of jumping into some of the details. The first one is the end-to-end supply network model. I have a screenshot of one of the supply network. Of course, it's kind of scrubbed and modified, but what you are seeing really is on the left-hand side is what we provide to our end user. It's more like an executable thing with the knobs that they can actually set and run. Because the way we have set up our team, we are more like a center of excellence. We develop, we work with our stakeholders to understand the problem. We partner with the subject matter experts to develop the solution. We test it. We do a proof of concept and pilot, and then we land it, and then we work with IT to scale it. And then it is owned by, the enterprises to kind of run this. And so that's why we want to make sure that we have the right selection of tools and ability to scale, integrate, and things like that. In this case, we also have an innovation, supply chain innovation lab where we get to test out these kind of solutions beforehand. And in this particular case, the important thing was, we were looking at a multi-echelon inventory optimization across the network. We were also looking at service level. So I think the network helped us to really understand where the constraints are, how we want to move the product, and what are the different things we need to manage. And so this was, we leverage it within the factory, we leverage it across the network, and we use it for various scenario planning as well as with the logistics operations. And the second one I talked about is the autonomous planning solution. And I want to make it very clear that it is not, like a lights out planning. We still have planners. We still have, like a strategy. We have like an LRP, long range planning. We have mid-range planning. We have execution. And primarily what it is in this particular case is we have a whole lot of data that comes in. And we have solver, the custom solver, with the complex event processing engine. We have the AI module with basically decision support. And the way it is operating is we have a data layer, and then we have a logic layer, and then the optimization. And then, of course, we do have a very well-defined visualization layer. And but we are trying to understand and explain. And in several cases, when we resolve, we don't have to go solve it if the solution is already near optimal. And that is where the artificial intelligence module is looking at what the decision was made, what has changed, should we even run it. So this has actually helped us in thousands of yearly planner hours that we can reinvest elsewhere. And the plan is more robust, more explainable. And we are, kind of targeting towards going towards 70 plus, like a % reduction in plan with this modules, and then going from 50% to 90% of product plan autonomously. And it also not only is planning, it is also providing a view of what and how the next scenario is going to happen, where and how, what needs to be done. So it is providing an early view of what's going to happen as well. So this has been implemented and with great success. And so you probably would have also seen in the latest Informs Edelman, this was one of the key solutions that was highlighted there. And then I was talking about contract analytics, and contract analytics is primarily looking at creating contract, executing contract, and closing contract. As I mentioned, we basically walk through what are all the different steps we need to do, strategy planning, authorization, negotiation, close, post-close, and in this particular case, digitizing it and making the data searchable and analyzable, and applying machine learning and natural language processing, and providing a dashboard that is user-friendly. Meaning what you see on the top right is primarily the green, and red is a combination of different clauses like assignment, choice of law, and things like that of interest by contract. Like our folks can look at it, and if it is green, they know that it is it is compliant, favorable. If it is red, it doesn't exist or it's not favorable, so that they can click down all the way to the contract so that they can really look at what is going on. And then I talked about predictive visualization. Most of you are familiar with the control tower concept. And what we are also looking at it is leveraging our, predictive, in this case, it is a time series kind of a model where we're really, applying it on the network to understand there's a given parameters, or like we're kind of projecting forward, saying how the inventory, like our days of inventory is changing in this particular example, for example, and if it is going out of control, then what we can do about it. And then we also are looking at leveraging, the heat map contrast. We're looking at thousands of these lots or SKUs at the same time to look at how they're moving. If there is an issue, it's clustering to look at where the challenges are, so that we can feed it to the control tower and actions can be taken. And as you know, I think it is supply chain visibility is a #1 priority, and we have been able to apply our predictive visualization for both internal and external data to get a better visibility. And the other one, what we have done is primarily, sourcing intelligence, and we're leveraging AI, ML, NLP. We primarily, talking to our sourcing folks, we kind of captured what are the different things they are interested in. Alternate supplier, like labor practices inconsistent, supplier technology maturity, where it's the right time to buy. So, market intelligence, material intelligence, putting it all together, we were able to bring in, subscribed as well as available data to understand what and how the market is moving. Is there an issue with our supplier? We also leverage external, like a sourcing intelligence to really look at if there is a natural disaster. We're integrating all those things. We are trying to look at, can we sense and respond? Can we mitigate the risk? And what we have done is we collected all that information. Primarily, it is an unstructured data, and then collating that using NLP and some of the internal feature analysis, we were able to provide, if there is a risk that we need to work on. And that can be what I'm showing on the top right-hand side is the tool, the output of the tool that our folks can use, and they can select, they can filter, and they can really look at what they can do about it. And they can also go down to the source of the data. And we also have a translation engine, basically, that helps us to pull data not just from one source, English, it also can be from Mandarin, it can be from Hebrew, and it converts and provides a very holistic data, like to insight. And so what is the value of all this work that we're doing? We were able to actually provide tangible results because of the work we have done, whether it is increased velocity, decreased inventory, in fact, it has been hundreds of millions of dollars, whether it is an equipment, whether it is the wafer. We were able to provide an optimal inventory to service level, and we were able to improve productivity and quality, and we have decreased significantly supply interruptions. And I haven't mentioned this, but some of our work, analytical work in helping supply chain and Intel overall has propelled us into the Gartner Supply Chain Top 25 over the last 10 plus years. And in addition, there are a lot of other, internal as well as external value that has been created. And I know I'm kind of running into my last few minutes. So we are all, living in this COVID era, and hopefully all of us are, safe, practicing safe habits and vaccinating, and, kind of hoping to put this COVID behind us. But from a supply chain perspective, what are the different things we have to make sure our supply chain and our analytics is helping to be more agile, whether it is a peacetime or wartime. Looking at it, we have to be ready for fast adoption. And then whether it is, so we have very defined metrics. So we monitor, we measure, and we control, and then we are staying on top of things. And then our advanced systems are helping us to really understand our supply chain better and plan for it proactively. And then commitment to embrace change, knowing what has happened or what's going to happen. We need to be able to have strategic engagement, whether it is with our suppliers or customers, and it's very critical that we have a right pipeline of talent and ability to learn from what has happened and what's going to happen. And then we have to have a very good business continuity plan, not just learning from it, but foresight. So what we have seen is supply chain has become, foremost critical and in the center of all the things. But in order to ensure we have, business agility, whether it is during past time, like a peacetime or wartime, we need to make sure a predictable, transparent, and prepared supply chain is a requirement. So with that, I'm going to bring it to the end, and I'm ready for questions.
Great. Thanks so much for the presentation, Manny. It's an interesting contrast because Intel is probably one of the most complex and advanced supply chains in the world, and I'm pretty sure they have a lot of PhDs, such as yourself, working on it and trying to improve it. Maybe unlike some of the retailers who are kind of maybe on the other end of the spectrum in a lot of ways. Okay, so just as a reminder to the audience, you can type your questions in the Q&A or on YouTube as well. So Elaine has a question here. Could you describe a use case or example and the value of applying a digital twin?
Great question. So to me, digital twin, primarily people say a lot of things about digital twin. To me, it is an extension of a simulation or a model, right? But a digital twin, where it differs is a simulation model most of the time is used for scenario planning, what ifing in the strategic space. Now imagine the same model, which is representing the real life, right? I mean, you can actually hang your hat on it saying, what I see in the model is what is actually happening. When you get to that level of credibility, now start connecting your operational data, start feeding your operational data into your simulation engine. Now you have two different things that are happening. One is a simulation is running what ifs, and it's giving you what is going to happen, the predictable engine. And on the other side, the digital twin is going to give you primarily what the data actually is happening, what are the operational things that are happening. And now it gives you a nice contrast between, it's learning from the actual data, and it is going to train the model to make it better. And now you can actually be using the model to design, to take, decisions and, plan your, the next steps. That is where the digital twin happens. The way we are looking at digital twin from multiple angles. One is from the asset twin, because some of our equipments are, hundreds of millions of dollars, when you buy them. So it is critical to understand how they operate. It's critical to get the best out of it. So we are actually creating an asset twin that mimics the equipment so that we can learn from it. This is almost similar to what GE has done with the aircraft engine, where they're pulling all the engine performance data and feeding it into their engine to look at, airspeed, looking at thrust and things like that. So we're trying to look at what are the internal losses. The other one is where we're building process twins, which is an extension of a network model, for example, for supply chain, to really look at how our supply chain is operating, how our factories are operating. So those are the examples that we have in digital twin.
Very interesting, and I'm sure it's definitely a challenge in order to
get
that
a challenge.
Quite right.
Exactly. Getting, number one, getting people to, say, yeah, this is the way I want to go, because what you see is what you get for a lot of people, and what you don't see is hard to believe. And once you develop the credibility, and then, it has happened, right? I mean, it takes time, but once people like the model, they believe it, it becomes a magic wand in their hand.
Yeah, and I think it's a lot of these tools are just about empowering the users in order to do their job better.
Exactly.
Okay, so Cameron has another question here. Is North America prepared for disruptions of the supply of rare earth and precious metals required for advanced manufacturing? I guess a more macroeconomic question.
Oh, that's a great question. In fact, we all had experiences with some of the rare earth, particularly, Toyota had challenges when, I believe it is palladium, or I'm trying to remember the one that is used in the catalytic converter was not necessarily available for them because, it was primarily available in China, and there were some restrictions that Toyota was not able to get their hands on. So that basically created them to really look at alternate sourcing, alternate supplier. So the question is, North America prepared for rare earth materials? We kind of deal with that. In fact, some of the materials we're using, metals we are using in our supply chain, in our factory for making semiconductor was not even invented. It was not in the periodic table before. So, like I'm proud to say that Intel, with the ability to really look forward into what we need to make, what are the things that are involved. We also have designed for supply chain team that is working with our, architects, our designers, and our developers, like from a product perspective to really look at, what are the performance requirements? What does the next transistor look like? What are the different metals and materials and chemicals and gases that need to go in there? Where is it coming from? And what are we going to do with that? And cobalt, for example, was an issue for us a couple of years ago. So we really looked at it from a strategic perspective, and we were planning for, what are the, like where the sources are, what the alternate solutions are. I'm 100% positive that many of the companies are starting to look at it strategically because they don't want to be, like handcuffed into, I don't have the material. And in fact, you all heard about the chip shortages that is happening across the board right now. That is one of the reasons why Intel is actually unleashing IDM 2.0, because when you look at how much of a semiconductor is foundries are made, 80% is made in Asia right now. So that means we got to be prepared for those kind of things. So the strategic thinking is there, but do we have the solution that is fully baked? No. Are we aware of the problem? Yes. Are we working towards that problem, resolving the problem? Yes.
Interesting, very interesting. Very, very relevant, I guess. Okay, so maybe one last question. Elaine has another question. Has Intel created or thought about creating an exchange type of market to treat digital twin models as assets? So then maybe you can exchange them or maybe be able to use, I suppose, in other applications.
I think that's a great question. Like when we create our solutions, we are number one internally focused around Intel needs. Then we are starting to look at the ecosystem. For example, the digital twin, what we are developing is very critical and applicable to Intel, like stakeholders. And where it would be useful would be if we kind of expand it out to our suppliers and customers. And then we can open it out to the ecosystem within the semiconductor. So currently we are operating, like it has not fully evolved to that level yet. So we are operating within Intel, within the innovation lab, within our stakeholders to, the models are proliferated. The digital twin is, is being developed. And then we are partnering or we're working with some of our equipment suppliers to get them on board. But we are not there yet in terms of taking it to the market.
Okay, very interesting. Well, thanks so much, Manny. Very interesting to see one of the world's leading supply chains and how they're using AI and data in it.
Thank you.
Thanks for your time. All right. So thanks, everyone, for attending, for those of you who are still on. And I want to extend a great big thank you to all of our speakers who had great presentations and gave us a view into how they're using AI and data in the supply chain today. And I just want a reminder that look out for more great events brought to you by the TD Management Data Analytics Lab. We're having these all the time, bringing industry experts to talk about topics related to data and analytics. With that, have a great day, everyone. And thank you for coming.